If you've looked at any of our stuff online, you'd have seen this, of course. It's all good, clean fun. Well, it is. It's not completely random. It's actually related to the things we'll start talking about today, of course. And so let's stop that. What else we got? This is so today we're about to start talking about fluid dynamics proper. Everything else has been so far really talking about statics, and but now we're talking about moving fluids. Even though we've been talking about accelerating fluids in statics, what we mentioned was kind of oxymoronic, because how can it be accelerating if it's static? But the issue is that it's not circulating. Now we're talking about fluids that are flowing, and so we need to be able to change gears a little bit to be able to deal with this. And so this is just one of the examples that we will use. If you've looked at the exams, there certainly was an exam question on this, not on the first exam, but maybe in the second exam, which is in the realm of what we deal with. I think it costs $155,000 for one of these, and it's kind of an interesting piece of equipment, the so-called jet lev, just a modified fire hose, I guess, but it's quite amazing the amount of power, obviously, you get out of something like this. So we'll do it to talk about how much, what the fluid velocities would have to be, for instance, to be able to lift you up, to be able to say what the size of the pump would have to be that would allow you to go at those speeds. And so we will talk about these as we go through. Can't remember when this was from. Maybe this was a couple of years ago, or maybe it was last year, actually. America's Cup. It looked like the Americans were going to lose, and they finally. This is Oracle, so I guess this is Larry Eliason's boat. Finally won the last of the, I guess it's a series of 7. So the winner who gets 4. So it's 3-3, and they pulled it out, I think, for the final one. I was reminded on the news the other day that maybe in 1983 was the first time that the America's Cup had been won by someone other than America, and the Australians won it. And if you look at the very first class we had these 3 slides of natural processes, recreation, and something else. In the recreation, we had a picture of a boat with a wing keel on it. And so at the time of the 83 coup, I guess, by the Australians to win, they used to put the boat in the water every time with a shroud on the keel, so you couldn't actually see what it was. And so what it was had wings on it, either to pull it down or to pull it up. I'm not sure, hydroplaning. And so these boats, of course, are fluid mechanics all around. Going through the water is fluid mechanics, but also the wind that drives it. And the sail is really almost like a wing these days, these rigid sails. And these things do hydroplane. They have little hydroplanes underneath the catamaran hulls, or is it trimaran hulls? Catamaran hulls that actually lift them up, as you see on the left-hand side there, to be able to reduce drag in the water. So amazing, amazing boats. So if you look at 10 years ago, they were all, well, I guess 83 is more than 10 years ago, but 83, they're all single-hulled boats and not catamarans. And these are 12-meter yachts. I'm not sure what 12 meters means. I think it doesn't mean that it's 12 meters long. It's some kind of complicated formula that dimensions all the different components. And so we will pass on to chat about fluid dynamics in the first of these. So maybe, as in previous sessions, we'll just kind of recap exactly where we are. Big picture is that you remember that we took this was the basis for us to be able to calculate the forces acting on structures. And the forces acting on structures were just a series of expressions like this, if it was static, which we've made the point is always true, and it matters whether unit weight, which includes density and gravity, whether density is constant with pressure or not. And so it's not constant with pressure for a gas, and is constant with pressure typically for a liquid, incompressible. And if we do that, we can use that to calculate pressures at a point just from, for a just by using this expression. And if we know what pressures at a point are, we can integrate that to get overall forces that are applied on structures. If we can calculate forces on structures, we can use that to say whether the structure fails in some way by taking moments or resolving forces against some kind of failure mode. And we talked about that in the material from last week. We know that in static fluids, fluid pressures are constant on any horizontal plane. That's not necessarily true in accelerating fluids. And if you remember, last time we talked about accelerating fluids, at least in linear acceleration, and we found out two things. One is that the slope of the accelerating fluid we can get from looking at the relative accelerations in different directions. And so clearly now this is not true, that this is the case. But we found out that in this case, the actually pressures would vary so that there are a whole bunch of contours which are parallel to the surface, which would be equipotentials, the same fluid pressure as you go down in depth. And from that, we could calculate what the pressures were acting, for instance, on the back side of this face, on both sides. And they varied as a function of the location of this upper point, and also on the magnitude of the vertical acceleration. If it was accelerating vertically, then the pressure would be increased, just like standing in an elevator and feeling the forces in your ankles as you accelerate to go upwards, or the opposite as you go downwards. We also took the same expressions, or developed expressions, for rotational accelerations. For something going around at a steady speed, the fluids on the outside of that rotation are obviously going around at the same velocity, same speed as it goes around, just as if you'd had a weight on the end of a string. It's going around at the same speed if you rotate it, but it's changing velocity because it's not going in the same trajectory. It's going in this direction at one stage, then as it's 90 degrees, it's going in the opposite at 90 degrees to that. And when it's going 180 degrees, it's going in the opposite direction, although at the same speed. And so, although in rotations, the rotation speed is constant, there's an angular acceleration, and that's given by the rotation speed in radians per second, its radius, and density. And so this is the expression that we use for that. And we found out in an analogous way that if you take a drum and you spin it around some kind of center line, then instead of being a horizontal surface, then you get this parabolic surface like this. And it acts in the same way that if you took actually equipotentials, just as in this they're parallel to the surface, the pressure changes as you go in this would be parallel to the surface. And we can do two things. We can figure out exactly what the surface looks like by looking at points on the surface and saying that the fluid pressures at all of these points have to be atmospheric. If they're atmospheric, they're all the same. And if they're all the same, then we can figure out this expression from that assumption. If we know what the fluid pressures are at a point, if we know what the free surface is, then we can actually use that to calculate what the fluid pressures are with depth. And in this case, we know that as you go down in depth, again from the free surface, if it's a liquid, then the only term that matters is this unit weight change with elevation, because we're sitting at any particular radius, but that radius here is constant for all of these values. And so that's our kind of understanding. So we did two things. Accelerating fluid, take the free surface, assume pressure doesn't change along that free surface, and if that's the case, we can calculate what its inclination is. Once we know what the inclination is, then we'd like to know what the pressure change with depth is, and we can do that by just solving a similar analogous equation. So those are the two things we solve for. So those are all in so-called static systems. It's accelerating, but the fluid in this tank is not circulating. It's not convecting in any way. And so that's different to what we'll talk about today. It turns out that when we're talking about fluid dynamics, we'll use exactly the same expression, F equals ma, to be able to derive exactly what's going on. And so what we'd like to do now is we'd like to say something about moving fluids, fluids that aren't static. And actually we can, as it turns out, we can use these expressions that we've already developed to be able to say something about it. And so we'll talk about fluids in two circumstances. And I'll just draw a little, actually not a very good diagram there. This is my attempt to draw an airfoil. And so we can look at two things. We'll define a streamline. And a streamline is just the trajectory that, say, molecules of the fluid would take as they go from upstream to downstream. And we can also define something that's normal to the streamline. My writing doesn't get any better, does it, this time? I think it might do. And so, in some respects, it's slightly analogous to this. So we're interested in being able to figure out exactly how, for instance, pressures and velocities change as we go along a streamline. So we're interested in this. And we're also interested in, if you go perpendicular to the streamline, how those velocities and pressures also change. So those are two things that we'd be interested to do. You're probably all familiar with Bernoulli's expression. I always write it this way. And so we've talked about many of these components. This would be a velocity. This would be a pressure. This would be an elevation of this point. So we've pretty much defined all of these terms. And you probably know that along a streamline, that those magnitudes have to be constant. You probably also, well, I'm not sure whether we do. I think we talked about it on the first day. We talked about how this is equal to this. And so this is the destruction of inertia term, or destruction of momentum term. And this is the fluid pressures and the elevations, which add to the force term. We can show that, but we don't really need to. And so this is Bernoulli's equation. And we can write it both along a streamline, which is what this is, to be able to define this behavior here. But we can also write it perpendicular to a streamline in a slightly different way. And so the reason of bringing this up here while we recap this is that we talked about linear accelerations when we dealt with the fluid pressures within a bath. And it turns out that we can use the same expressions that we had to derive the expression along a streamline. And if you think about perpendicular to a streamline, if you think about going along this pathway that goes over the wing, you can imagine it as driving a car along the driveway where you go over the top of a hill and come down the other side. You know that you go over the top of the hill, you'll be forced out of your seat by centripetal force. And so in the same way that we talked about this idea of swinging a weight around your head, and analogous to being the centripetal rotation of a fluid that you're rotating in a container, then it won't come as any surprise that we can actually derive Bernoulli's equation normal to a streamline basically from this expression here. So that's kind of links what we've talked about statics to where we're going to talk about in terms of fluid dynamics. So that's our task for what we'd like to do today. Okay? So let's give a little bit of background to what we're doing. There's 5 pages of derivations, none of which we'll use, but I'll just introduce fluid dynamics and the requirements for fluid dynamics. Well, we said a little bit about it already. We're interested in being able to take a path of a fluid particle or a molecule, and we can write behaviors of what the fluid pressures and velocities might be along that path. The requirement for using Bernoulli's principle is it needs to be inviscid. In other words, the viscosity has to be 0. And that's sometimes met, sometimes not met. For liquids, you'd think it perhaps isn't met. For gases, you think it is quite well met. But we can use it, we typically use it for both liquids and gases. And there's some other requirements that are met, have to be met as well. It has to be incompressible. In other words, You think that you can't apply it to gases, but we do apply it to gases. It actually works reasonably well for gases. So strictly speaking, we shouldn't do, but it actually gives reasonable results for that. It should not have eddies and turbulence in it because it doesn't actually work in that particular case. And so that's one case where it doesn't work. And it should always be steady flow. So steady flow doesn't mean that everywhere within the fluid the velocity or the pressure has to be the same. It just means that if you look at fluid, say, going across a weir, and this top line might be a streamline, and also this bottom line here might also be a streamline. It's saying that the conditions at this point here, its pressure and its velocity and say its elevation, is always the same. So if you take a snapshot now, the pressure at this point is equal to whatever. If you take it in 10 minutes, it's equal to the same thing. It doesn't mean the pressure here has to be the same as the pressure here and here along the streamline. It just means that at a particular location, it doesn't change. And so that's, by definition, the steady requirement. If, for instance, this water level was being drawn down over time so that it became less high as time went on, it wouldn't actually satisfy this requirement of being steady state. So those are the requirements that you can do. For those of you who deal with fluids in porous media, we've already said that Bernoulli's equation is equal to a unit weight, pressure divided by unit weight of the fluid, and elevation. Typically, we refer to these as hydraulic head plus v squared over 2g equals constant. And so if you're solving problems in porous media flows, then typically the velocities are so small that we put this term equal to 0 and we don't consider it. So anything that you do in petroleum engineering or with environmental systems engineering and contaminant transport and hydrology, we use exactly the same expressions for hydraulic head, but usually the velocities are so small that we don't have to include the term that includes v squared because it's vanishingly small. And what is important is that in porous media flows, the whole essence of the problem is the viscous drag that the porous medium puts on the fluid that's going through these tiny pore throats. And so the essence of porous media flows are that they're viscous, and for that reason, we can't use Bernoulli's equation because it violates the fact that we have these viscous losses. I always use this analogy for viscous losses as pulling my briefcase across the top of a desk. To get it from A to B, I have to put force in it, and then it rests there. To get it back to the place where it started from, I also have to put force in it again. And so it's dissipating force by friction against the bottom of that component. And that's basically friction. And it's the same friction that acts within a fluid. It's a viscous loss. It's a frictional loss that we have to account for. And so that's what we will deal with when we're talking about fluids in porous media. So we could spend 4 pages deriving this, but let's not. Let's do something else. Let's do it in a bit smarter way. And so let's derive it in a much more straightforward way. Because I'd like to actually not just quote the result, but I'd like to actually pull it out of a hat. And it's quite straightforward. The idea is this. Imagine we have a streamline that goes vertically upwards in the z direction. And what we could imagine is that we have a little packet of fluid here and a little packet of fluid here. And we'll call these 2 different locations. We know from what we've done before that for static fluids, we can write an expression which is something like this. Change in pressure with elevation minus density times gravity minus density times an acceleration in the z direction is equal to 0. Bless you. I can write this which we also have seen. So it just comes from F equals ma, Newton's second law. And so this is for a static fluid, but the static fluid you could imagine is going from point 1 to point 2. This bucket of fluid, this differential volume, is moving up there at some velocity. And so the fluid at this point would have a velocity 1, it would have a pressure 1, and it would have an elevation 1. And at this point it would have a velocity 2, a pressure 2, and an elevation 2. So it's just changed its location. Bless you. They don't have to be the same. So what could we do with this? An acceleration is what? It's a change in velocity in the z direction with respect to time. Right? That's just by definition. We could also write that as a change in velocity in the z direction with respect to time multiplied by 1. Right? dz is just 1. And so that's convenient because if we do that, what's this? This is now velocity in the z direction. So this is just equal to change in velocity in the z direction with location multiplied by velocity. And if you trust me, we can always derive it, but if you trust me, this is also equal to a half you can show that that's the case as well. And so this is all by way of saying is that this is an acceleration term, right? We talked about it being linearly accelerated in our linear acceleration systems. It's written with respect to time, but what we can do is we can change it in a definition that is a change in velocity, not with time, but with space. So this is only saying that at location 1, you're going at some velocity v1. But by the time you get to location 2, you're going at some different velocity, potentially. And if you're going at some different velocity, you have to accelerate it to move in space. And if you have to accelerate it to move in space, then you have to provide a force to do that. That's what Newton's second law basically says. And so what we can do is we could substitute this back into this expression, and we have an expression now which is minus change in pressure with elevation minus density times gravity minus density times a half change with z of v squared. We could multiply everything equals 0. We could multiply everything by dz. Should have left some more space. And if we do that, we get rid of this. And so we have this. Just writing exactly the same expression out as before. This and this we get rid of. If we do these derivatives, then this ends up being, if this integration, not derivatives, integration. Right? So you integrate and you don't substitute limits, then you have to equal a constant on the right side. Constant may be positive or negative. And so that's Bernoulli's equation. So I'm going to divide both sides through by unit weight of fluid. This is still a constant divided by unit weight of fluid. Doesn't matter what the constant is. And so I can make these positive, right, if I wanted to. And I don't know, Bob's your uncle. Don't use that expression here, maybe. Is equal to z. And so this is, of course, something which is should be moderately familiar to you. Bless you. So that's good. So again, just to reiterate, this is mass times acceleration. These two terms here are force. We've done something, we have a constant, so let's not worry too much about it, but that's the genesis of it. That's where it comes from. And so that's all Bernoulli's expression is. So since we know that this is constant, then we can write it at point 1, and it should equal some constant. And if we write it at point 2, then it should equal the same constant. And that's the way in which we use Bernoulli's expression. And you've probably almost certainly used it in your past to be able to solve some problems. And so the essence of Bernoulli's problem or equation is to be able to write it at some location upstream, write it at some location downstream, and make sure that you only have one unknown to be able to do that. If you have two unknowns, then we can do other things like invoke conservation of volume to be able to get an extra equation to constrain it, which we'll talk about in these next 2 weeks, this week and next week. But we'll use that to solve a problem. And so let's use it to solve a problem. I'm not sure what else is in the notes. So in doing what we've done, we've worked our way through this, we've worked our way through this, worked our way through this, we've worked our way to this, and we've ended up with this. I guess a couple of things worth noting, right, is that this is the expression that we have now. This is Bernoulli's expression. It's no different from the one that we just wrote down. I guess the other thing which is worthwhile noting is that going to get to this point here, we also went through a different equation before we integrated it. And so sometimes this equation written in this way is quite useful. It's written in this way as a useful equation because we said that, strictly speaking, we can only apply Bernoulli's equation where it's incompressible. But we sometimes try to do it when it's compressible. And a typical compressible flow would be airflow around a wing to look at lift, the Venturi principle or the lift principle. And so in a case where the density of the fluid is a function of fluid pressure, then it may well be that this isn't a constant that we can include. And so that we may have to include this as a variable where maybe you use the ideal gas law to substitute into this, where the pressure and density are linked in some way. And so the two forms in which we'll use this equation are in this pre-integrated form and in this post-integrated form. And if you look back, I don't know if any of you are using these equation sheets, then these are these two expressions here. Yes. Not quite developed, right? But this is the other way to think about it. And so think about it in that mode. Okay? So that's kind of an aside, but we will use that. And so the idea is really quite straightforward. And the idea is that if you can look at a streamline from upstream as it goes downstream and goes around down here, then if you look at the magnitudes of the different components, then it's really saying that as you sum up an elevation head, a pressure head, and a velocity head, that they all sum up to some constant. And one way to think about that is that if you look at any point at any particular location, then the elevation of that is given by its location relative to some datum. And the height above it is the sum of these two other components, one of which represents the fluid pressure and the other part represents the velocity. And so if this was actually a liquid which was traveling, then the fluid pressure would be just the height of the fluid above that particular point. This is the pressure distribution as we go down here, not the velocities, but the pressure distribution as you go down here. And if it's flowing, then it has to have some finite velocity. And you can do that at some other point downstream. Again, the elevation of this point would be z. and the height above it to this same line, which has to be horizontal and parallel to the datum, then the magnitude of these two other components would be the sum of these pressure head and velocity head terms. And so sometimes the interest that we have is being able to sort out which part of this height here, this length, by definition, since it's a length, this has to be a length, and this has to be a length, right? They're all lengths. By definition, which height of this represents the fluid pressure, and which height of this represents the velocity head. And so if this was the surface of the fluid as you go down here, then with some reservations, we could say that the fluid pressure at this point is going to be this height multiplied by the unit weight, which is really what this expression is saying, right? If you write this out as Z, or if we write this out as H is equal to P is equal to H rho G. Pressure is equal to a depth multiplied by unit weight. That's really physically what this measure is. And so this just comes from this definition. This is a length, which is the pressure head, if you like. And this pressure head, if you multiply it by unit weight, gives you a fluid pressure at this depth. And we could see here that since this free surface now is lower, right, this length here is lower than this length here, then what does that say about the velocity that's going through here? If you have a big, wide, tall channel and it's going at some velocity, the flow rate is equal to the product of the velocity times the area. If you have that same flow rate going through here downstream, it's going through a smaller section, and so it has to speed up to get through that. It's like traffic going down a street. If you get a constriction, to keep the same number of cars moving, they have to be going faster through that constriction. And so in other words, we'd expect that the velocity head here would maybe be larger than the velocity head here just because it's constricted. So we'll try and rationalize those behaviors as we go through this. Again, a simple description of this as well as this example in the book. I will talk about this very quickly just to make the case that we could look at these three individual terms here. And so what are the terms? An elevation head, a pressure head, and a velocity head. So if we look at the magnitudes of these and how they are at each of these points, then what would that be here? Here, fluid is getting squirted out of this syringe. You're getting the air out of the syringe, and you get a trace of fluid out as well. This has reached the top of its arc, so the velocity you'd think would be equal to 0. You'd think the pressure would be what? It's in the atmosphere around it, and so it has to feel atmosphere. And the elevation is quite high. And so if you look at these terms here, this is a large number, this is 0, and this is 0. And these summed together have to equal some magnitude. If you look at this point here, what's it doing? Well, let's look at number 1 actually. Look at number 1. What's happening here? It's in the container, you're reefing on it. It's got a fluid pressure because it can't get out fast enough. And so here you'd expect that the fluid pressure would be high. Sorry. What would be the velocity? The plunger's, yeah, you've read it right. Plunger's moving very slow by definition, and so it has to be slow velocity. And the elevation is the lowest that we are, and so this is small as well. And likewise, if you look at here, again, what's happening? This has to be at atmospheric, because it's got, if you look at the fluid around it, the pressure here has to be atmospheric, right? Pressing against it. Since we know that the fluid pressure acting in all directions has to be the same, then the fluid pressure in this fluid stream has to be a similar magnitude. And so if we look at this point, then the fluid pressure we think is 0. The elevation is not very big either, but it's getting squeezed out of a small orifice. the flow rate that's being pushed by this plunger moving slowly here has to be exactly the same volumetric flow rate out here. And so since it's going out of such a small orifice, it has to be zipping down. And so the idea is that if we could figure out the conditions at either one of these 3 points, and that we know 5 of those variables from the 6 possible components, we could figure out what the 6 was. Yes? Where here? Which is where? This one here, you mean? Yeah, it's small. So if you want, I can write that in. Well, this is the direction, so yeah, it would be a small number here. It's fine. Okay, strictly speaking, all right? So that's it. That's all we do. So maybe worthwhile doing, see if we can do it. So we did this thing for the jet engine. And so what would we do here? No, I've got to have a bit of humor, right? So, let's do it. Let's do this one. Let's do this. So let's choose a point, point 1. By convention, let's choose points 1 and 2 as upstream and downstream. So Z1 plus P1 over gamma plus velocity head has to be equal to Z2 plus pressure head over unit weight plus V2 squared over 2G. So what do we know? We know that Z1 equals Z2. What else do we know? We know from our previous discussion about the pressure at this point here that P atmospheric has to be acting perpendicular to it. And so if P atmospheric is acting perpendicular to it, then the pressure within this stream, some small distance behind this engine, not in the engine, pressure in the engine is probably quite high, but this is probably going to be small. And if we're using atmospheric as gauge pressure as our reference, then atmospheric pressure is 0. And we don't know what the velocity is. Maybe. What about here? Well, here if the fluid hits here and then goes around it, so that by definition, the stagnation point, which we'll call it, V2 has to be 0. Hit me in the chest, right? You're standing there. The velocity was going at some big velocity before it hit you. In fact, it'd be going at the same velocity as V1 if it doesn't spread out as it hits you. But as soon as it hits you, it's going at 0 because velocity is a function of both speed and direction. And it's now going up against my face and going down to my feet. And so it's changing its velocity. And so the velocity here is 0. And so if we put this here as 0, we have this term. And so what we have out of that is that V1 squared over 2G is equal to P over rho G. And so that may be useful because if you want to calculate what the force is that is being applied on this car, then if this is, I did this before, maybe 10 feet by 10 feet, I don't think a car is quite that size, but then this is 3 meters by 3 meters, so this is about 10 meters squared. Force is equal to pressure times area. And so if we can calculate what the pressure is, then we can figure out what the force is that's applied on there. If we know what the force is that's applied, then maybe if we know that there's a block sitting here and there's a force that's applied and the car weighs 1,000 kilograms, and maybe the friction on the base, then maybe the force to actually move it is equal to Antoman's law, which is friction coefficient times the weight, which would be equal to mu times 1,000 kilograms times g. Right? So if we calculate what pressure is, then we have something to be able to solve this. And so we can just rearrange this in terms of pressure. So we multiply both sides by rho g, and we have that pressure is acting is equal to density times g times v1 squared over 2g, and we start figuring out what these terms are. And we can do the calculation pretty easy. What's the density? What's the density of air? Something of that order, 1.2 or something. It's something of that order. So we know the density of air. What's the velocity, you think? So you can constrain it if you think about a plane. A plane would go, perhaps you don't know this yet, we'll deal with it. The plane can only go as fast as it's kicking air out of the back of the jet engine. So at steady state, it would be roughly, it can be as much as the speed of a jet airplane. So speed of a jet airplane is maybe 500 miles an hour. So the velocity is of the order of 500 miles an hour. I think that's about 250 meters a second. And so now we could calculate the pressure is equal to 1 kilogram per meter cubed times velocity squared, which is 10 to the 2 squared meters per second, rounding down 250 to 100. I can do that. Just to give you a ballpark, it'd be a factor of 2.5 squared off, right? But that's all. And divided by 2. And so you can calculate what that is. It's going to be equal to 10 to the 4 pascals, which is 10 kPa. And so if you know this is 10 kPa, you know what the area of your car is, you could calculate what the force is. You know what the force is, you could calculate whether it makes sense that it gets blown away. So it's simple calculations. So that's Bernoulli's equation. So it comes from just knowing what accelerations are within static fluids. That's what we derive it from. It's really an application of Newton's second law. It implies that if we can calculate along a streamline what the components' behaviors are upstream and downstream, so long as we know 5 out of 6 of the terms, we can solve for the 6th, which in this case was this. Okay, thanks very much.